MIT. Larry did, I'll read off the list of many amazing things that you've worked on, including variational inference methods for graphical models. Came up with the Markov processes and curves technique, worked on local linear embedding or perhaps manifold enfolding, mixed memory Markov models. I'm probably forgetting about 15 things. And now he's come up with another new, and it sounds very interesting technique called discriminative mixture modeling. So here's Larry.
Okay, thanks very much. Thanks for inviting me down. And I hope this will be a very informal talk. Please feel free to interrupt. It's really work in progress, and therefore all suggestions and comments, criticisms are very welcome. I should say, this is joint work with Dan Lee, who's at Bell Labs right now. So I was told by Jeff that I'm speaking to an audience of specialists, so I'm not going to get a lot of hairy details, but I'm going to review the background material fairly quickly. But the basic outline will be to go over sort of standard traditional methods for using mixture models for classification, standard algorithms, why they're used so much and why we're looking for better ones, and to talk about a particular discriminative approach that we've been working on. I'll sort of sketch the main tools that you use to prove the convergence that this algorithm actually is improving a cost function at all the steps, and then I'll give some empirical results at the end of the talk that say why the algorithm's working and where it needs to be extended. So the traditional way that I'll refer to how these mixture models are used is as generative models. That is, they're used to parameterize joint distributions over feature vectors and their class labels Y. So you have a huge training set, and maybe there's two different classes. Sorry. Oh, yes, I'll have this problem. Yes, I can do that. So for example, you have a data set with two different classes of data indicated in blue and red, and you're trying to model each distribution, each class conditional distribution by some mixture of basis functions. And this is really just going to set the notation for the rest of the talk. You have some basis functions indexed by J. You have some mixture weights that are positive, and that gives rise to some class conditional distribution. When you're interpreting this as a generative model, that is, you want these distributions to be things you can sample from and generate new data points if you wanted to. You have to impose these constraints, namely that these basis functions are well-defined probability distributions, that these mixture weights are positive and sum to 1. And typically, what most people use in many applications are just Gaussians, either with a full covariance matrix or some kind of restricted covariance matrix if that's too expensive for each of the basis functions.
Is the idea that the basis functions will be shared across the class?
So I'm allowing for that in the notation in the sense that every class can make use of every basis function, but if you didn't want to, you could just sort of restrict that weight matrix W to be block diagonal. Okay, so we'll allow for that. Although there are certain advantages if you don't allow sharing, and certain ones if you do. So the traditional algorithm for training these types of models is the expectation maximization algorithm, and it's optimizing the joint log likelihood of the data. And this algorithm is widely used because it has a lot of nice features. For the case of Gaussian basis function, it has very simple closed form updates. There's no tuning parameters such as learning rates. It has guarantees of monotonic convergence. That is, every time you iterate these update rules, they're guaranteed to increase this objective function. And if the basis functions aren't shared, or if they're shared weakly, let's suppose they aren't shared, so every class has its own set of basis functions, then really this problem just breaks down in doing an independent mixture, training an independent mixture of Gaussians for each class. And so, if you imagine you have a lot of data, a lot of different classes, this really breaks the problem up into a much larger set of much simpler problems. And so that's why they're widely used and at least give a very good baseline, quick baseline for initial performance. But the disadvantage is these models aren't optimized for classification, and it's really easy to see why they don't necessarily perform as well as models that are specifically trained as classifiers. So the way you classify in these models is by appealing to Bayes' rule to compute posterior probabilities for a particular class label Y given some unknown test example. And the problem is that, and the way these models are trained is that the mixture basis functions for each class is trying to model typical examples, because there's so many more of the typical examples than the atypical ones. And so it'll tend to concentrate its basis functions where the typical examples are. So many times that works out quite well. So for example, in this scenario where there are two classes, and I might put down basis functions here, I'm going to get this decision boundary in green, which looks very close to something like the optimal decision boundary between these two classes. But if you look at this next example, where let's just suppose I'm going to model each class by one Gaussian, then all the typical examples are concentrated in these clouds, and that's where I'll put the Gaussian basis functions, and I'll draw the decision boundary here. But I'd really like to draw the decision boundary here. That would give you much better classification. And you can see that it's just these sort of atypical examples in the red class that are pushing it there, but they're going to be basically washed out by this maximum likelihood EM technique. So that, in a nutshell, is why we'd like to consider models that are trained by optimizing a more discriminative cost function. So really the motivation for this work was, is there an algorithm for discriminative training of these models that has same advantages as EM, or maybe some of the same virtues as EM? Maybe it's impossible to get all of them. And there are a number of algorithms out there for discriminative training, but we weren't satisfied with them in terms of maybe some of them relied on gradient methods and you have to set learning rates, or some of them had unspecified constants that needed to be set, and theoretical bounds for setting them were very weak. So the idea here is basically to move away from from focusing on typical examples of what I'll call learning prototypes. That is, if these are Gaussian distributions and the mean represents some typical cloud of data, moving away from these class conditional distributions to just focusing on what the distributions you're really going to use for classification, these posterior distributions. So what I want to just start from this point. I'm going to have some matrix of mixture weights. I'm going to have some collection of basis functions, and all I care about are these posterior distributions. Okay, and let me relax all the constraints that are necessary to make them well-defined class conditional distributions, only impose the constraints that are required to make this a well-defined posterior distribution. Okay. And that's going to give us some additional freedom, which we can exploit if it helps us to design an easier learning algorithm. So as I mentioned before, when you're treating these mixture models as generative models that you want to sample from, you have to impose these normalization constraints so that they can be interpreted as proper distributions. Well, we can relax these constraints to what I'll just call non-negativity constraints. But I'll require that my basis function, when I evaluate it on some point x, it returns some non-negative number. But there's going to be no requirement that these numbers integrate to 1. Okay, so my basis functions don't have to be they don't have to be, just densities. They don't have to be unnormalized densities. They can be things that don't even integrate to some, they don't have to integrate to some bounded value, for example. And also on the mixture weights, I'll require them to be non-negative, but I'll drop the requirement that they sum to 1. And as long as we're forming posterior distributions using this ratio, just requiring them to be non-negative will result in numbers here that if I sum over I, the class label on the left, it gives me a valid posterior distribution. What was that? No, because all I'm summing over here is the class label, not the feature vector. I'm always conditioning on the feature vector. So what this means if you're thinking of using Gaussian basis functions, that I'm no longer really requiring the covariance matrix to be positive definite. Okay, and that has some interesting interpretations that I'll get to later on.
Do you show that it's non-singular?
It could be. Well, okay. The matrix being singular doesn't actually make this computation non-singular. No, so we don't require that either, actually. As you'll see, that issue doesn't really come up in the way that we parameterize these basis functions. So we have to obviously use some different criteria for training, and I'll just refer to this under the very general label of contrastive learning, but it has many many different names depending on the community that the various algorithms have been proposed in. So we imagine we have some, this again just set notation, some data set of labeled examples x and y star of n is the correct label for the yth example. And then I'll define some indicator matrix, capital Y, which is basically just a binary matrix, and for each example it has a 1 in the column, or sorry, a 1 in the row that indicates which class it belongs to and zeros everywhere else. Now for our objective function, we'd like to maximize not the joint log likelihood, but the conditional log likelihood that given data point in our training set that we classify it correctly. And because again, we're focusing on this posterior distribution, which is a ratio, well, the log of the ratio can be written as the difference of two terms. So the important thing is why I call it contrastive learning is that we get two terms that are competing against each other. And the first term is exactly the term that's optimized by the EM algorithm, but it's the second term that makes things interesting and problematic in some ways and difficult. But what the second term is doing that's interesting, it's coupling examples with different labels. So right away it seems that when you go to any form of contrastive learning or discriminative training, you're going to lose one of the big advantages of the EM algorithm, which is that you sort of can train all the, if you're not doing any sharing basis functions, you can train basis functions for one class independently. That seems to be unavoidable. So now we'll see if can we keep the other advantages.
Could you say that again?
Yes, yes. If you're using the EM algorithm and just maximizing the joint log likelihood, which is this term, you can basically look at each class one at a time. Just look at all the data for that class and build a model of data in that class. Okay? And the parameters for that model aren't affected by data in other class. When you want to do discriminative training, though, essentially you not only want the basis functions that sort of define one class to be attracted to the examples in that class, but you also want them to be repelled away from the examples in the other class. And so now every basis function really needs to be trained on all the examples, at least in principle.
So what you're saying is that even if I decided to make Wij block diagonal, it will still hold that
That's right.
example of class X will influence the W's of class YZ.
That's right. Now, it could turn out that, you know, for some examples, they're so, easily identified in one class that numerically they have very small influence. But you have to evaluate that sum to know that. So that's why it makes the problem more difficult. Okay. So there are two sort of sets of parameters that we need to optimize. There are the mixture weights, and then there are the basis functions. Let me first start with the mixture weights, because this is really the cleanest result that came out of our work, which is that there's an extremely simple mixture weight update rule that has the following form. You have this cost function that's a difference of two terms. Basically, take the derivative of each term with respect to the mixture weight matrix, and it's very easy to verify that each of these derivatives is always a positive number or a non-negative number. Okay, so both the numerator and the denominator here are both non-negative. Take that ratio, multiply by your current value of the weight matrix, and use that to reset the mixture weight matrix, and do this all in parallel. And now if you take my word for it that these terms are both always non-negative, and you initialize the mixture weights to be non-negative, then you can see that because this update rule is multiplicative, it automatically preserves non-negativity. Okay? What's not so obvious, but actually true about this rule is that it actually leads to monotonic improvement in this objective function for discriminative training, this conditional log likelihood. And so that's a nice result. And is there an easy way to understand what's going on with this update rule? And actually, this update rule has a very intuitive interpretation. So, imagine that I just wanted to derive the simplest possible update rule. I might start with my cost function and just write down a gradient rule, right? And move the parameter in the direction of the gradient so as to increase the objective function. Okay, so my overall cost function is this log likelihood L. It consists of two parts, L plus and L minus, so I get that difference. And now I have some learning rate eta that I want to set. Let me just choose, out of the blue, a learning rate that depends on my current parameter and on something else, which is inversely proportional to the second term of the gradient. Okay. Now that seems like a strange choice, but as I indicated before, this guy's always positive, these are always positive, so that definitely gives me a positive learning rate. When I do that, this gradient ascent rule basically collapses to this multiplicative update. So we can see the multiplicative update is just actually a gradient rule, but where the learning rate is somehow been chosen in a way that guarantees that I always actually take not just that I always go uphill, even when I'm taking a finite step as opposed to just sort of an infinitesimally small step. And it's easy to see that this learning rule has the same fixed point as a gradient rule, because the only way I'm going to be at a fixed point is if these two terms are equal, and if these two terms are equal, then the gradient is 0. Okay? So if it converges, it's going to converge to some stationary point. Since you're always jumping, unless you're extremely unfortunate, you're always going to be jumping to a local maximum. Well, you could get, if you're really unfortunate, stuck in a saddle. Why this learning? I don't have a good one. I mean, it's fairly intuitive why you'd want things to scale with the size of the weight. As you get smaller, you take smaller steps. Why you want this is a little mysterious, but that works out to give the same update rule. Okay.
So you have a derivation that shows that even if it's not.
So we have a derivation that shows that this always leads to an improvement of the objective function, and then this just sort of pops out at the end, sort of identifying it after the fact. It can be interpreted this way.
Maybe you said this, but is it the case that even if you have a local maximum, you might jump around at the end? Typically, learning rates, you might not have a schedule.
You won't jump around. This is a problem with the EM algorithm too, right? And it's possible that your objective function could be a saddle, sort of look like, like this. So there's some point here that's flat. And in the EM algorithm, you could sort of jump from here to here, and then it's a stationary point, and you'll just get stuck. This has the same property. It never happens in practice, but that's why you can't say it converges to a local maximum. You can converge to a saddle point, but you don't oscillate around it there.
Okay. Can you guarantee that with this learning rate, like there are some constraints for grading the ascent rule, where you have like the sum of the learning rate should be go to infinity, and the square of the learning rate should be bounded.
Oh, those are for those are for online rules. So in other words, if you're looking at one data point at a time, and then you ask what are the conditions that doing this over time that all eventually converge, then you need this thing where the learning rates sort of shrink with each iteration, so as you get closer and closer to them. So this is a different scenario. This is basically, we're looking at all the examples one at a time and just trying to go a batch routine that jumps up in the overall conditional log likelihood at each step.
So what's the guarantee that there will be meaning there will be a finite learning rate even before it reaches a limit point? Like in an optimization scenario, like you need all those conditions on learning rate so that you guarantee an improvement before it reaches a limit point. Because like it might be possible that it reached the limit point and your learning rate is 0, so you have no improvement at all.
Well, I don't mean to claim that you will reach the fixed point in a finite number of steps. Okay. In other words, this choice of learning rate can and does get slower as you get closer and closer to the fixed point. Okay. So maybe I just need to be sharper about what I'm saying. So I'm not trying to say that, basically the guarantee here is exactly the same as the EM algorithm in terms of its convergence properties. It might take a long time to get there, especially if there are sort of some weird, Hessian that has some very odd singular values. But at least at each step you're going up, and you don't have to worry about tuning a parameter like that. So that's the main virtue, and that it has a pretty simple form. So now let's talk about the basis functions. And what we really hoped was that there would be a rule like that for the basis functions, and we were disappointed that we haven't found one. So first, to talk about the basis function, we have to say how they're going to be parameterized. And like I said, they're required to be strictly non-negative, or make them be positive functions, but not normalized. So we'll basically parameterize them the following way. There'll be some parameter vector, which I'll call omega of j for the jth basis vector, and the basis function will just be, some exponential in some feature vector that I'll call capital X. So capital X could be the same as small x, or it could be some expanded representation of this vector. So as sort of a simple case to consider where that might be useful, imagine that this capital X is not only the original feature vector X, but consists of all the pairwise products of the elements of the original feature vector, and maybe also you throw in just unity as one of its elements. And then by choosing this feature vector in a carefully crafted way, you can basically reproduce a Gaussian basis function with this parameterization. So that just means if I've trained a mixture of Gaussians model, I can always use that to initialize this model by setting my omega vector based on the means and covariance of each Gaussian. Now, of course, this model has a lot more freedom because I can define many omega vectors that can't be parameterized in this way, or that if you tried to parameterize them this way, would give rise to covariance matrices that weren't positive definite, or such as like that. Okay, or that were singular.
Can I ask you about the previous result? Did it rely on the mixture rates not summed to 1? Or does
It does not enforce that constraint.
it doesn't enforce it?
Of course, you can always, after the fact, the model has a freedom, which is that because the posterior probability is computed as a ratio of two terms, if you take all the mixture weights and then just scale them down by some factor, you don't affect that ratio. So if you wanted all the mixture weights in your system to always sum to 1, not just for a particular class, but for all across them, you could always just divide and that wouldn't affect anything.
If I wanted to do it
For a class, it does not enforce that constraint. And it doesn't usually wildly violate that constraint either in practice, but it definitely does not enforce it. Okay. So like I said, we were really hoping to find an update rule that had a very similar form to the previous one, sort of a multiplicative update in maybe these parameters or the exponential of them. We didn't find that, so we decided to look for, to use a similar intuition from the previous problem, which is, well, let's write down a gradient descent rule, okay, and then ask, can I find learning rates that actually guarantee that I'll improve? Now, there's a very trivial way to do this. So here's my gradient descent learning rule for now. For each basis function of parameters, I take the gradient. This is going to be some positive definite matrix that rotates the gradient, but don't worry about that for now. You don't need that for the result I'm talking about. But I'll have some learning rate that's specific to those basis function parameters. Now, of course, there's a very sort of trivial way that I can compute these learning rates that will guarantee improvement, and that's just to say, well, set the learning rate to be 1, take a step with that learning rate, evaluate the objective function, did it go up? If not, halve the learning rate, did it go up? If not, and just keep on halving the learning rate. But, and I'll call that sort of a line search approach. But that's not really an accomplishment because if you have this huge data set and every evaluation of the objective function means you have to loop over all the data points, then to set this learning rate, you're spending as much time as you need to compute the gradient. So that we consider to be, that's not really an achievement beyond just stating a gradient descent algorithm. What we really want is a learning rate that we can compute that doesn't involve an indeterminate number of evaluations of the objective function, okay, or an indeterminate number of passes through the training examples at each iteration. Okay, so it turns out that we can do this, and let me just give you a flavor of the things you need to compute that enter into the learning rate. So the basic things you need to compute are what I'll call these weighted responsibilities, and they're, you might consider them something like the analog of the posterior probabilities that you normally compute in the E step of the EM algorithm. But this looks like a very complicated beast because it has 3 indices, but just I is the class label, J is the basis function label, n is the example number. And basically what you're doing is you're saying for this particular class and for this particular basis function, how much does it contribute to the overall sum that's used to normalize the posterior distribution, okay? So compute all of those guys.
I have one question.
Yes.
Like when you do the normalization like that, how do you constrain the size of the weights? Because if that's scale invariant, because I scale the weights, all the weights with the same number.
Yeah, so, okay, so, yeah, I mean, we never really had a problem with that in terms of them running away. Of course, you wouldn't, I mean, unless you run into numerical overflow, you're not even going to notice it because it doesn't affect the cost function at all. But I think that after every iteration, we just said, okay, let's make all the weights sum to 1. Since it doesn't change anything, you can always throw that in afterwards. Okay. So you compute those responsibilities. And basically, all these matrices and learning rates are, once you've computed those, these guys are pretty easy to compute. So these positive definite matrices actually have an interpretation as Hessians. Sorry, this slide is kind of faded. As Hessians of the auxiliary function that you use to provide a bound on the original objective function. But the important thing is that they're positive definite matrices so that you can invert them. And the way you can see they're positive definite matrices is that all these responsibilities are positive, and this is just some weighted sum over all the examples of outer products. So that's going to give rise to some positive definite matrix. And the learning rates are basically for each basis function, you have to do a very simple one-dimensional minimization over the interval 0, 1. Basically what you do is you collect a few statistics of this distribution formed by those weighted responsibilities. So, I have a set of positive numbers. I can always turn them into a distribution by just dividing by their sum. So let's call that, for every basis function, let me compute this distribution. Let me call that rho hat. And then alpha j, beta j, and gamma j are just statistics of that distribution. So I only have to loop over the data set one time to compute each of those statistics. And some of them can be computed in the same loop. So this is why you don't have to loop over the data set an indeterminate number of times to set the learning rate. You do it a finite number of times to compute these statistics, and then you just have to optimize this function, which is very quick once you've computed these numbers. You could, if you really wanted to make it quick, you could just sort of have a lookup table that, given the value of alpha, beta, and gamma, gave you the optimal value of eta in that interval. But a one-dimensional minimization, there's very quick routines for that. So that determines learning rates. Plug that in, and you're guaranteed with that learning rate to improve the objective function.
Is there a geometric artificial computation of doing this? Especially the should be the Hessian.
Yeah. So let me see how I can put it. Okay. So you have yes. Here's the geometric interpretation. You have an objective function, which is not convex or concave or globally anything like that. Okay. But you essentially you're at some point on it, and you construct a concave approximation to it around that point, okay? That actually provides a bound on the true objective function, okay? And you compute the Hessian based on that concave approximation. That's going to give you something positive definite, okay? That's basically where the Hessian comes from. And then if that approximation was extremely good, then basically, if it was extremely good, you would probably end up setting this learning rate to be 1. In that case, you're just sort of doing Newton's method, okay? But if this concave approximation is not extremely good, you need to scale down the learning rate. So you're basically finding sort of an automatically enforced value that makes Newton's method convergent. But it's not Newton's method on the original objective function, because the original objective function isn't concave, okay? That's the best intuition I can give for that rule. Okay. So now I'm not going to get into details of the proofs of convergence, not because they're tricky at all, but I'm just going to, there are basically three bounds that, or inequalities that one uses to prove the convergence of this method. And the basic idea for proving convergence is the same as the EM algorithm. You're going to try to construct an auxiliary function that has these sorts of properties that, so the original objective function has, is a function of the parameters. You construct an auxiliary function that is a function of two sets of parameters. It has the property that if the arguments are equal, it reduces the original objective function. And it has the property that if you alter the second argument, you always get an upper bound. And then by some manipulation of these inequalities, you can always prove that you're increasing the objective function. That's a very high-level argument. But if you're familiar with the EM algorithm, then the following inequalities that I'm going to give you would basically allow you to, I think, derive the algorithm that I just presented. So the first inequality, I'm sure everybody here is familiar with. It's Jensen's inequality. It's used in the exact same way that you use to derive an auxiliary function for EM. You have some log of sum of positive numbers in your true objective function, and you can bound that by taking, by introducing some probability distribution P over N and replacing the log of the average by the average of the log. Okay.
Quick clarification. So the first inequality will have to be guaranteed by your upgrade rule, and the second one will have to be guaranteed by the nature of Q.
Yes, that's right. That's right. That's right. That's right. That's exactly right. Okay, and just as in the, so this inequality is basically used on the first term of the objective function in the same way as the M. So these P that you're introducing are the posterior probabilities that would enter into the E step of the EM algorithm. Okay. There are two other inequalities. The first one is very simple and is actually proposed for this discriminative mixture modeling a couple of years ago. But it's just a very simple bound on the logarithm, a tangent bound using Legendre transformation. So the log is a concave function, so at any point you can upper bound it by its tangent. Okay, and I think that bound is pretty easy to see. Yes.
It was proposed by them to use for discriminative.
It's been used in many different contexts. Yeah. Yeah, yeah. I think it's been used before that. If you look at some derivations of iterative scaling, improved iterative scaling, it appears in there. It's been used all over the place. But these guys did use it for in this context, so I wanted to note that. The next bound is something that I'm sure it exists in some journal of inequalities, but we repeated the derivation ourselves. I haven't found it anywhere. But it's an easy bound to derive. I'll derive it on the next slide. But this is sort of the reverse Jensen's inequality. And the bound basically is assume I have some variables. This is going to correspond to the learning rate eta. So it's between 0 and 1. And what I'm denoting here by these angular brackets are expected values of this random variable. So the classic Jensen's inequality, right, is that expected value of e to the something is greater than e to that expected value. Okay. Basically, to deal with the term, the new term in the objective function for discriminative trig, I need a bound in the opposite direction. And so this bound, opposite bound, has the following form. Basically, you have the same prefactor out in front, but obviously you need something greater than 1 here to flip the side of inequality. And what you get is something that is always greater than 1. And it depends on the expected value of something that's e to the quadratic in the original random variable z. So this bound, just to be clear, this bound can actually be vacuous, right? Because this, this expected value could be defined, this guy could be defined, but this expected value could be undefined, okay? But in the case that we're working in, if z is a sort of a discrete variable, or one that can only take on a discrete number of values, then it's always defined. And that's going to be the case we're interested in. We're basically going to be doing an average over training example. Z is going to take a particular value for each training example. So this right-hand side is always going to be defined. And this is only guaranteed to be a bound if eta is less than 1. And you'll see why that comes in later. And I think this is just for some random data, just to give you an indication that, as eta goes to 0, that's where the bound really becomes extremely tight. So let's prove this bound because it kind of looks mysterious, but it's. Yes. Why is it only? You're going to see why it's only guaranteed for eta less than 1 in just a second. Okay. Because the proof is 4 lines, so, and that's one of the steps. Okay, so let's just, I'll state the reasons, and I think this will be easy to follow. Normally I wouldn't do this in a talk, but I think this will be easy to follow. So let's just rewrite the exponential of e to a to z as just an algebraic identity, the sum of 2 times the cosh minus the exponential, because cosh is just 1/2 the exponential plus its inverse. Okay, so that's just an identity. Okay, on the next line, I'm going to keep the second term the same, so I just have to prove this thing. And by just looking at the Taylor series expansions of cosh and the exponential, you can actually show that the exponential of the square of the argument over 2 is always an upper bound on the cosh. Okay, so that's just a function identity. Okay, the next line, here's where we're going to take advantage of the fact that eta is less than 1. Okay, so if eta is less than 1, then we can just think about e to the z squared over 2 as being some random variable that we're taking an average over, and this is a concave function of that random variable because I'm raising it to some power that's less than 1. And since it's a concave function, I can upper bound it by taking the expectation of just that variable and doing the function on the outside. Okay, so that gives me an upper bound, and that's the place where I lose it if eta is greater than 1. And in the last step, I'm just going to use the normal Jensen's inequality, but now I have a minus sign out in front of this, so it's going to allow me to preserve the upper bound. Okay, so hopefully you can see that that's actually pretty simple. Now that's not the exact form of the bound I had in the last page. To get the form down here, just take this random variable z and replace it by sort of the random variable where its mean is subtracted out. And if you do that, basically what you'll get up here is the difference between z and its mean, and this other factor will pop out in front. Okay, that's just some very simple algebra. That is the so those 3 bounds actually give you the auxiliary function and allow you to prove the convergence. Really beyond that, it's just bookkeeping with indices. Yeah, really, it's not complicated. Did you have a question or?
Yeah, well, when you in the equation you had for could you just explain how the equation you solved the learning rate?
Oh, how it relates to this? Yes, excellent. Okay, yeah, I can do that. I wish I had 2. Okay, so it relates in the following way. The auxiliary function, okay, for the algorithm basically becomes a term like this plus a term that is linear in the learning rate. Okay, so sort of fixate on this term for just a second. I don't think I can do this. I don't think I can put them both up. Can I? Oh, yeah, okay. Oh, yeah, there we go. There we go. Okay, so this term here is right here, okay? You get and then this is the linear term. And so you start with some objective function, you get a bound on it, and now you basically want to choose eta so that it improves.
Linear in eta, because on the left side it's
here it's not.
e to the eta.
Yeah, here it's not linear in eta. This comes out of the bound,
Right.
but there's some other term that is linear in eta. That's from the.
That's not from the left side of the inequality.
No, that's not from this inequality at all. That's just some other part of the objective function. I mean, if you just took this term, it's clear that to maximize it, you just set eta equal to 1. So that there's clearly got to be some balance, and it comes from this term.
The objective function starts with a linear term plus the term on the left, which then you use the bound to get to that thing.
That's right.
And you maximize it.
That's right. That's exactly right. That would have been a much better way of saying it, too. Did everybody get that? I could say that. I should say it since everybody can hear me a little bit better. The objective function starts with a term that's linear in eta plus a term like this. Okay?
So maybe back up one slide and put up the objective function here.
Okay. I don't think, well, okay. Absolutely. At your disposal. But, we've abstracted away quite a bit, so I'm not sure how much putting up the objective function will help, but yeah, I'm really not sure that much. Why don't I keep going? I can come back to this. I can redo some Blackboard stuff because with these amount of notes in front of me, I can reproduce everything. That's why I say it's not so difficult. So how does the algorithm work? I mean, this is a proof of convergence, but it could be that in practice, you're always setting eta to be very close to 0.0001 and getting nowhere. So I should say also that in practice, mixture weights give you very little bang for your buck in terms of how well they improve the discrimination. It's really the basis function updates that are doing almost all the work. I think that most people are familiar with that if they've done any sort of discriminative training. So the first thing we tested it on is a very well benchmarked set of handwritten digits that's available at AT&T. So there are 60,000 examples of handwritten digits in this for training and 10,000 for testing. And you can see there's a considerable amount of variability in these digits. And some of them, if I asked you to identify what that was, or this had the blue, you might not say a 5. So it's not clear that you should really be able to do perfectly on this set. So the models we trained in this case, we basically, after some pre-processing, we trained all the models using maximum likelihood, because that's a very good way to get a cheap initial point. And then on top of that, ran 64 iterations of this algorithm. Okay, and those are some curves showing, as a function of the iteration, basically what I call it here is the log loss, but just the minus of the conditional log likelihood, and how that's going down. And then, really you're not usually interested in that conditional log likelihood. You're using it because it's sort of a smooth objective function. Usually you're interested in the error rate. So the second curve just shows that the error rate is actually, in some ways tracking this log likelihood function, even though it's not explicitly being optimized.
So the one on the left is on your training sample.
These are both on the training samples, right? Now, you definitely expect this to be happening. It could be that this is, doing something funny. So that is just sort of reassuring.
To get a feeling for this, how many basis functions were there, and like how many dimensional?
I'm gonna get all of that. I'll get all of that. Yeah.
What were the range of the stereos? I mean, did you actually get like close to 1,000?
What were the range of the in the end?
The class scores?
They're usually, well, I mean, most cases they're pretty confident about. Most examples are pretty unambiguous.
So you got
One of 10 classes, yeah. But in certain cases, you can, the decisions made by this algorithm tend to be a lot softer than what you would get by just doing a maximum likelihood model. Okay, so let me get a little more into the numbers so people can sort of see how many parameters there are and things like that. Okay, so I'm going to show not just training examples, but test data as well. So there are 60,000 examples to train on. Okay, we used a certain number of basis functions to model each digit. Okay, so to make it sort of analogous to the maximum likelihood case. And these are the error rates as a function. M is the number of mixture components per digit class. Okay, so this is basically a single prototype per digit trained by maximum likelihood. The error rate was about 10. When you apply the discriminative training, the error rate was basically halved on the training data. And the last column shows the total number of parameters in the classifier. That doesn't change as you do different types of training. Okay.
Wait, so does the bottom row mean that you're getting 1/10 the error when you have 32 mixture components?
On the training data.
Oh, okay.
Training data. I'm going to show test data later.
And also, what is the dimensionality of little x in a problem like this?
Okay, so raw dimensionality, let me say a little bit of how we train this. So the raw dimensionalities are 20 by 20 images. So X would be 400. Okay, X would be 400. What was then done was a principal components analysis to basically reduce that from 400 to 40. Okay, and then all the covariance matrices in this case were diagonal. Okay, okay. So every basis function had about 80 parameters. 40 mean 40 variances, or 80 other sorts of, they're not, you can't interpret them as means and variances, but something like that, okay? So, you know, you can clearly, you're always doing much, much better on discriminative training, but I mean, the obvious question is, do you start overtraining? And so we'll show them. Yeah, so in this case, for every sort of, to compute the score for a digit, you rely on a certain set of basis functions, and then you normalize it by computing that same score for all the digits.
So it's not surprising the way that
Not surprising.
it's not surprising that the way that
Oh, yeah, they don't, but even in the case where we've tried sharing, they don't end up doing too much. It just turns out that for you have high dimensional data, I think this is more a function of dimensionality data. If you have high dimensional data, basis functions tend to be become very peaked, and so the dynamic range of them is just much higher than the mixture weights.
Again, this is nitpicking, but the 810 in the first case, is it, in case of the GMM, that's really 800, right? Because the mixture weights are 1.
Yeah, okay, that's true. So there are.
In case of the second one, there really are. These are not 0, 1. So in other words, they could be
Yeah.
W.
But to further your nitpicking, if I had just not even trained on the mixture weight, I'd have gotten the same result. It's all in the basis functions.
So ignore the last two.
Yeah, you can ignore the last two digits if you want.
Why did you mixture weights in the GNM? I missed that, sorry.
So in the there's just one mixture component per digit. So
in each of those cases?
in this case, no, in this case, in the first case.
Only in that case.
So that's not really a trainable
Just making sure I
parameter.
understand the number.
Okay.
Yeah, it's just
This is a sanity check.
you just yeah. So okay, so now maybe I can even do this. Keep those up. Okay, yeah, I can do that. That works. Okay, so now I can compare training and test. And basically, again, on the test examples, you do find that you are getting improvement. But you also find that the improvement is not nearly as dramatic when you start getting these much larger models. You start overtraining much more quickly.
What's the best number that you can possibly get? I mean, like if you do 64 mixture components or 328.
On the testing?
Right, the numbers are still going.
But the GMM is still improving.
Oh, I think you can get down to, let's see, you get down to about a little over 3 here. Yeah, you get down to a little over 3. So, okay. Yeah, the rule of thumb we basically found was that this is only for this data, but basically if you look at the number here and then multiply the number of parameters by 8, you get something comparable. That was kind of on training and test. So 1 here did as well as 8 here, 2 did about the same as 16, 3 did about 4 did about the same as 32, same in training. I don't know why that seemed to hold, but that seemed to hold across these examples.
Another practice over there. So how did you stop the GMM training?
Oh, there was really no effort. The only effort at sort of avoiding overfitting was just to show these results for various different model sizes. All the models were basically trained to convergence. Yeah. There was some flow-on variances and things like that, but all the models were essentially trained to convergence. So, I mean, the big win here doesn't, I mean, yeah, this was pointed out, the big win here doesn't necessarily seem to be that you do better in the sense that your raw score is better at the end if you're willing to throw as many parameters as you want for the maximum likelihood model. The big win is that you do better with a smaller model. Okay. But if you're going to use very large models, you have to be prone to overtraining. But these results suggest the regime that you should be working in if you think these models are going to work well, for these models to work well. And that's really the regime where you have lots and lots and lots and lots of data. And And so you're not too worried about overtraining. And you do actually want small model sizes because you are worried about speed and efficiency. In other words, you want as much, you want the system to classify as quickly as possible, but you have way more than, data than you can afford to train a really huge model on, okay? And in some ways, that is a regime of speech recognition, which is why we weren't, why we thought these results might be encouraging, right? Because you're not going to throw, even if you could improve performance by going to 1,024 mixture components in the speech recognition system, you're probably not going to do it.
Can you refresh my memory on the number of iterations it took for this to converge?
Yeah, this was 64.
64. So at each iteration, you have to evaluate all the Gaussians and all the data.
Oh, yeah. Well, let me show you the curves. I mean, it's converged. The convergence is rapid at first, right? I mean, you probably didn't have to go to 64, but
Right.
it's not like, I'm aware in speech recognition, discriminative training on these big systems, 1 or 2. Yeah, I know. Yeah. So yeah, this is expensive. There's no getting around that. But you get the most bang at the beginning, I would assume.
So what was the training procedure? Did you start at each number of mixtures from an ML training system, or did you?
That's right. Yeah, because discriminative training is inherently more expensive, so it just doesn't make sense to start from a random starting point. Okay. Let me say a little bit about why it's interesting to relax these constraints on the basis functions. So one of the nice things about this digit example is that you can basically, when you do maximum likelihood training, plot the means of each mixture component, and you can see that they correspond to prototypes, typical digits that are trying to model some of the variation data sets. So for example, this 6 is it's a thin version of the 6, there's kind of a loopy version, here's a 7 with a bar in it, etc. Now you can do the same thing after you've applied discriminative training, but of course, the basis functions for discriminative training, while you can cast them in the form of a Gaussian, if you interpret what the variances are, some of them might be negative, okay? So in other words, you could have some directions that are sort of, in other words, you want to be close to this mean in certain ways, but far away in others. You get more credit by being far away from this mean. So you can actually learn, instead of learning, what might be called prototypes, you can actually learn what you might want to call saddle types or anti-types. In other words, in order to be classified as a 1, you want to look like, one of these guys, but you also get a lot of points if you don't look like this guy. It looks like a 0.
So that's interesting. Have you tried any experiments where you start out with training a maximum likelihood system, not just on the prototypes, but on the anti-types?
Well, so in these cases, if you were to look at the covariance matrix, you would find that it's not positive definite. So it's unclear how you would sort of use that to see the maximum likelihood model. If you just kept the mean the same, but then made the matrix positive definite, it would have exactly the wrong effect.
I meant like invert the value of the pixels in the original images.
Oh.
One before you train the Gaussian. So
Oh, I see.
you have some Gaussians that are modeling like anti-1.
Oh, I see. Maybe
So
sort of
if you
take
start
the image and, yeah.
So that you start out with some guys like the first row, second column.
I see. No, we didn't do that.
So what are we looking at here? Is this like you take an 8-mixture system and you take the mean from each system?
This is like, yeah, so in the generative case, it should be very clear what we're looking at. We take for every digit, we have an 8-mixture component model, and we're just plotting the mean of each mixture component, which corresponds to an image.
There seems to be some big contribution to the variance, the fuzziness, I believe, that corresponds to the...
So the fuzziness corresponds to the variance. And so that's another way you can see that these models are much fuzzier than, these are very sharp. This is why the decision boundaries in ML-trained models tend to be very sharp. They tend to be overconfident in their mistakes. You get a lot of fuzzying here, as well as these opposition effects. Okay, so I mean, it's
Fuzziness isn't good. You're not going. So you said you do PCA, right? To get the 45.
The fuzziness isn't due to PCA, because otherwise it would kind of show up here too. So we do enough PCA.
So this anti-tightness is so interesting. Is there any reason to believe a priori that you wouldn't? It seems to me that you would believe a priori that you would get the best results with an equal mixture of tights and anti-tightness as your basis function. Is there some reason that that wouldn't be true?
I think.
Which would indicate, I mean, if you take that supposition, that would indicate that what happened here is that you started out with only tights, so it was never able to overcome some kind of a local minimum.
So I mean, my intuition is slightly different, which is that you basically want the basis functions to be representing examples close to one or the other side of the decision boundary. Okay, kind of like support vectors, to use a choice of words, but so I don't really have an intuition whether more of them should be on one side or the other. You know, I might suspect that in a 2-class problem, your intuition seems like it might work a little bit better. But in a 10-class problem or a many-class problem, it seemed like you're going to need a lot to be on the right side. But the one thing that's interesting about this, because there are many discriminative algorithms out there that don't relax these constraints, that basically, you know, they go to a lot of effort to make sure the variances remain positive. Is to show that if you do relax these constraints, you know, you get something. I mean, the algorithm wouldn't be going in this direction unless it was improving the cost function, right? So you're getting, this is allowing you to classify better.
Did you ever try initializing it not from the maximum likelihood initial starting point?
Yes, but I don't, not on this data. Just because this data took like, you know, overnight to train from a good starting point, and I probably should have done it from just a random starting point,
Yeah.
just to see like what the
It
might look really, really different. Yeah, that's actually worth doing. Should try that.
Another question. In what you presented earlier, the W matrix was not required to be block diagonal.
That's true. Here it is.
Here it is.
Here it is. Or, I mean.
I was going to say, what is that picture?
Yeah, so I did do the following experiment where I started using a matrix like this to be block diagonal, train this likelihood model, and then sort of, instead of, you know, basically made all the 0 components in that block diagonal matrix, not even epsilon, actually kind of big, and then let the discriminative model take over. And very quickly, the mixture weights that sort of were initially 0 but perturbed, they went to 0 very, very quickly. So it didn't, I was kind of disappointed. That was the way I really thought you'd end up getting a lot of, you know, of these repelling effects, was that, you know, this class is actually using all these guys. It didn't seem to happen too much. It could have been a function of the initialization. Maybe if I initialized everything randomly, I wouldn't have biased the solution so much.
You mentioned here, did you say you were disappointed? I mean, I would have thought that how they put this out in the maximum likelihood. It's kind of surprising that these prototypes are so simple.
Yeah, I guess.
The 7 prototype, I mean, of course, pictures are not anything to go by.
I mean, you definitely get some that are fairly similar, but so my suspicion is that some of these prototypes, what's happening is that, let's take a really typical one, like a 7, this 7 here, and this 8 here, which is just totally unambiguous. I suspect that these guys, they almost play no role in discrimination.
Yeah, I mean,
They're not even necessary.
Can you do some sort of an error analysis or try to determine in what circumstances individual components actually fit the balance in the decision?
I mean, they're sort of, I think you know, you could try the sort of, first thing you try is look at the basis functions and, you know, check their ratio to the other ones, but we haven't sort of systematically examined that. How am I doing on time, by the way? Am I?
Another 10 minutes.
Okay, I can definitely do that.
We could spill over. We don't eat lunch till noon.
Okay. I'm not going to spill over. I hate doing that to people, but I don't
No,
I don't have material to do that anyway. So.
I mean, we did have another 15 minutes
Oh,
for
okay.
discussion, so you could always, since we did discuss
Okay.
stuff already.
Let me get to this because this I think will interest this crowd. Okay, even though it's, like I said, very preliminary. So we wanted to test this for speech recognition, and I'm just going to say we did this in the most brain dead or boneheaded way. Okay, which was just to I'll describe the task later. Let me just describe how we applied the algorithm. We didn't do it in any sort of intelligent way in terms of treating things as data points that came from some continuous data stream that were being embedded in a hidden Markov model system. We just said, the usual way you train maximum likelihood models in speech recognition is someone gives you a segmentation, all the data points belonging to a particular phoneme or part of a phoneme, substate of a phoneme are grouped together, and you model them with a mixture of Gaussians. So now let's just train, all the states against each other. So if we have, 100 phonemes and 3 states per phone, then we have 300 states, and let's just treat this as a 300 class classification problem, okay? And train the things that way, and then we'll get a sort of a frame by frame classifier, and then there are ways to take a frame by frame classifier and by normalizing the posterior probabilities, sort of insert them back into a HMM classifier, the way that was done using neural networks, 10 years ago, okay? And we just wanted to see how that would do. It was sort of a logical first thing to try. And so the data we tested this on was a connected digits task, not a noisy task, not a ward, just some connected digits that AT&T has. So a fairly large amount of training data, almost 1 million frames of speech. I mean, not large by speech standards, but enough to get a good idea of what's going on. Test data was 11,000 and a half utterances, and the baseline systems were just, straightforward, context-independent HMMs. This is not this would probably be, by today's standard, be considered small vocabulary, well, definitely small vocabulary, but also a small system since it's context-independent. And here's what we found. We started with a weak baseline, which is we just used n mixture components per state, and then we did 16 iterations of discriminative training. So this first column is the maximum likelihood mixture model. The second column is the skewered mixture model. And the first chart just says the frame error rates, okay? So this is the thing we'd expect to really go down, because this is what the algorithm is actually optimizing. And in this case, those error rates go down by quite a bit. They don't look like so much. Remember, this is like, how many, I think there were something like 120 states here. So this is a 120-way classification. So when you see absolute reductions in the error rate of around 5%, that's...
What are the frame answers?
What are the...
The answers, the frame answers.
What are the reference? Where were they provided from?
Yeah.
Oh, by some segmentation that's been used.
Provided by system or what's the...
Yeah, provided by like the best trained system on this data. And the best trained system on this data is actually very good at AT&T.
What's the word error rate for that system?
Connected digits, it's probably like one or close to 1%.
And of course, since it is used as reference, its frame error rate is 0.
Yeah, its frame error rate would be, well...
I'm just thinking if we were to put those numbers...
No, not its frame error rate. No, because it's frame... No, because it's a forced segmentation. It's from a forced segmentation, right?
Direct constraints.
So yeah, so the true recognizer would have a higher frame error rate, okay. But then I said what we did is we took these posterior distributions, divided by their prior probability of being in each one of these states, according to how much data there was in the training set, plug that back into a recognizer, and saw how the word error rates. And for this weak baseline, I'll tell you what a stronger baseline was. We did see some improvement. Actually, decent improvement. So we were encouraged by that. But this, like I said, this is a weak baseline because, like I said, if the very best system, context-independent discriminate train, get down to 1%, we're not operating anywhere near that yet.
Can you see a way of doing this without relying on a better system?
Without, for segmentation? Not immediately, but that would be something to talk about.
Why not just iteratively segment your
Well, okay, you could, so I guess assuming the subtext to your question was, in a way that's always improving some cost function in the background. So yeah, you can always iterate, but I need to think about that.
It's not
Yeah.
straightforward to change the regular MMI training criteria to use your update.
Let me get back to that question.
I mean,
That-
the reason why I asked would be
right.
exactly this situation as well. We can talk about that.
Okay, sounds like we should do that. Maybe offline with that, but in a larger group. So let me just show. So one very easy way to improve this baseline is is to just up the number of mixture components for silence. Keep everything else the same, but more mixture components for silence, because there's a lot of different types of background junk in this data set. And what we found when we did this is, again, the frame error rates go down consistently, but now the discriminative training, it didn't seem to help much. And we attribute this essentially to the fact that we're not optimizing the right thing. There's really no reason why this should follow this trend.
But the best digits result is MMI training, and the best published results is the digit set.
This isn't TI digits, but yeah. But the best, the best results, like I said, would be down at 1%. There would be several things different. First of all, they'd be doing context dependent, so that would cut you down by a lot. And then they would use some form of MMI or discriminative training, but where the objective function for that training is a word error rater, or is an objective function at the sequential level. It's not a frame by frame objective function. Okay. So the reason we don't think we're seeing this is because it is a frame by frame training algorithm. And that's really where I wanted to close, because we think we have an algorithm, by all indications, for the cost function it's supposed to be optimizing, it's a very good way to optimize it. You can start with models that are small in terms of the number of parameters they have, and this really seems to get as much discriminative, bang for the buck on those parameters as you can. It has nice convergence properties. It's easy to initialize. You get these decision rules that exploit not only prototype effects, but these sort of repellent effects from what I call them saddle types or anti-types. But the real question is there a way to take this algorithm and now extend it to HMMs? And so, that's basically an open question. We're still really thinking about that.
So I have a question about
yeah.
the handwriting recognition results. Was that system state of the art?
Oh, our current, let me put those results back up. Yes and no. Yes with qualifiers and no. Right, okay, so let me put that back up. Okay, so how competitive are these results? So the best results on this data set are, again, hover just above 1%, okay, on the test set. But what are the systems that do that? The systems that do that are support vector machine, which if you look at sort of the time to classify or the amount of the model size that you need to keep around, it's really huge. It's like you're storing like something equivalent to like 1/10 of the data or something like that, okay? So, so there are also very good results by a very large neural net that just use some form of early stopping. But again, if you look at the number of parameters in that system, it's on the order of like, over 100,000. So, and there are better results for systems that make use of prior knowledge, so like tangent distance sorts of classifiers. So it's not state of the art in the sense that there are better systems, but in terms of if I tell you, okay, I want a system that has this many parameters or has to classify this quickly, and I put on those constraints, and then I say don't use prior knowledge, and with those constraints, it's extremely competitive. It's extremely competitive.
But could you extend your system to take the same number of parameters as, let's say, support vector machines? How well would it do that?
Then you'd overtrain. need to overtrain. So support vector machines, there's some really clever theory behind them, which is why they can get away with without overtraining.
You can always falsify it as a support vector machine combination to reduce the parameter size to the same amount that you're getting over there.
Yeah, but you probably take a hit then in terms of your error rate too, right?
Yeah, of course. How much?
The question is how much. Right, right. I mean, so the main reason for investigating this particular way of parameterizing a classifier is because if you have, like I said, it's good for a particular regime. Okay, the regime is lots of data, lots of classes. If you have lots of data and lots of classes, you're not going to want to use a support vector machine, right? Just and you're going to want to get an initial model very cheap. And the way to do that is to use maximum likelihood learning because it factors the problem into so many different things. And so that's the regime that this sort of thing we were hoping would be good for. And so.
Indirectly, doesn't it depend on the choice of basis functions? Like in support vector machines, it's independent of the choice of independent of the choice of basis functions. But here, if you choose the basis function wrong, for example, I choose the exponential distribution, like instead of a Gaussian machine model, and I start discriminated training after that, it won't give me the same results. Because there's some, indirectly in choosing the basis function, you're using the prior knowledge. Meaning you are choosing.
Yes, to some extent. I'm sure there are choices of basis functions that are just horrible, but I think it's easy to see the context in which this was performed. Gaussian mixture models are just so widely used, it makes sense to investigate discriminative approaches on top of it. So, that's about all I'll say why I think it's interesting. Yeah.
So have you done a side-by-side comparison with MMI for Gaussian mixture models? Or
Well, we know the results. MMI is really optimizing correct. You mean on speech or on the digits data?
Not anything, just so you could take your same objective function and optimize it. And you can even compare the two different
Yeah,
relationships side by side.
I think we haven't done that. I think the results would be very similar. The only thing I think would be different is just that and we don't have to set a learning rate. Really, the whole reason for this was we didn't MMI did sort of a gradient-based approach. We didn't want to have to deal with the setting of a learning rate.
So you think MMI is a gradient-based approach?
The implementations I've seen, maybe there are other ones that I'm not aware of. And there's also these extended Baum-Welch update rules, but there again you have to choose this parameter in there to sort of guarantee.
It's very much the same thing. You choose the parameters, so
No,
you get updated in the right directions, basically.
No, I think the parameter in that case is chosen to ensure that the variances remain positive.
Exactly.
But the theoretical, in practice, you don't end up using something that's actually guaranteed to improve cost function. At least that's the way it's done at AT&T. Because the thing that's the value that's guaranteed to lead to improvement is too small in practice. So you usually choose something bigger than that. So. Okay, that's really all.
Thanks so much.
Okay, thank you.